Okay, welcome back. Now the video I'm going to solve a problem. It's called pressure inside of a planet. So I'm going to show you how to calculate the pressure inside of a planet as you go into the planet due to the weight of the planet, right? Due to the weight of the part of the planet that is above you pressing down on you, right? So let's first assume that model the Earth as a uniform planet, right? Uniform density. Then we can do a planet that is non-uniform. Right, so let's say you are inside of the planet here, distance r. So what would be the pressure at that distance r inside of the planet? So what we have to do is we have to take spherical shells, and we have to say what is the weight of that shell? What is the weight? So the pressure caused by that spherical shell is equal to the weight of that shell divided by the surface area of that shell, right? So the surface area, because remember, pressure is force over area, right? So the weight of that shell is equal to over area A, right? So the weight of that shell will be equal to that mass of that spherical shell, dm, times the gravitational field at that location, right? So the g at that location of r, right, divided by the surface area. So this is going to give you the pressure just due to that one piece, right? We can call it dP. Then I'm going to have to integrate over all of those spherical shells all the way from r to big R, and the big R is going to be the radius of the planet, right? So then what's dm going to be? Well, dm is going to be rho dV times gravity g over area, right? So since we're doing the uniform density first, we can have the rho be constant, and then we can do non-uniform density, right? So then the question we're going to ask is, what is the gravity g at any location for a uniform planet? And I've done a video on that earlier, right? I have a video where I show that the gravity of a planet at any location is equal to gm over r cubed r. Okay, so the gravity increases linearly from the center all the way going up to the edge. When the little r is equal to big R, the gravitational field is equal to big R over r cubed equals gm over r squared. Okay, so then when you get to the surface, the gravitational field is just simply equal to the gravitational constant g times the mass of the planet over the radius of the planet squared, which it should equal, because after that the gravitational field drops as 1 over r squared, right? So we see from this equation that the gravitational field increases linearly as you get farther out. So this shell will have a larger gravity than the shell that is inside of it, right? And it's also going to have a more mass. The dm is going to be more because the volume of the shell is going to be more. So not only is the gravity going to be more, the volume is going to be more, right? So then we can say here, this is the density rho. dV is equal to 4 pi r squared, okay, dr. That's the volume of a spherical shell, times the gravity is going to be equal to gm over r cubed r, right? And then we divide this by the surface area, which is equal to 4 pi r squared also. So notice this 4 pi r squared, the 4 pi r squared cancels. This top 4 pi r squared is from the volume of a spherical shell. Then you're dividing that by the surface area of that spherical shell. So then these two cancel, okay? And then you're going to get dP is equal to rho gm over r cubed. And then you have here r. Okay, and then you're going to integrate this from all the way from wherever the little r is all the way to big R, right? Because when you're at a certain location here, all the pressures of all the spherical shells above you are all pressing down on you, right? All of that pressure is pressing down. So we're integrating all the way from the little r all the way to the radius of the planet, right? And then you have here r, and then you have here dr, right? dr comes from the volume of a spherical shell. So then we can integrate that. Okay, so then we're going to integrate this, and then we're going to get the pressure is equal to rho gm over r cubed, right? And then the integral of that is going to be r squared over 2. R squared over 2 from r to r. Then you're going to have here rho gm over r cubed. R squared over 2 minus r squared over 2. Right? And then we can put down what the density is. The rho is equal to the mass of the planet divided by the volume of the planet. Right? So then it's equal to the mass of the planet divided by the volume of the planet. Then you have here r cubed. So this rho is just m over r 4/3 pi r cubed. Then we can factor out the 2. Then we're going to have here r squared minus r squared. Okay, so if we simplify that a little bit more, the pressure is going to be equal to what? You're going to have here gm squared. Okay, the 3 will go up to the top, right? And then 4 times 2 is going to be 8. 8 pi r to the 6th. Or what I could do is I could take, make this, since this is r to the 6th, I can write it as r to the 4th, and then take r squared and put it inside of the parentheses. So then I'll have here 1 minus r squared over r squared. So this is the pressure for a uniform density planet inside of the planet, right? So what does that's showing you? If the pressure at the radius of 0, right, at the center of the planet is going to be the greatest pressure, right? So then when r is equal to 0, you're going to have this. Okay? This is going to be the pressure at the center of the Earth or of the center of any other planet whose density can be modeled as being uniform density, right? And then if we put little r is equal to big R, what's going to be the pressure? Okay, then it's going to be equal to, you put your 3 gm over 8 pi r to the 4th. So we put 1 over r squared over r squared. So of course 1 minus 1. When you get to the surface, the pressure is 0, right? Okay, how about if you are halfway inside of the planet, halfway in? Halfway in, you get here 3 gm over 8 pi r to the 4th, 1 minus a half squared, right? Because the little r is equal to half of big R, but then you have to square that. So you get here 1 minus a quarter. 1 minus quarter is going to be 3/4, right? So 3/4. So the pressure halfway into the Earth is going to be 3/4 of the pressure at the surface. So let's do some calculations, see what this is equal to. So let's say the Earth can be modeled as a uniform planet. The big G is this value, right? Value are Newton meter squared per kilogram squared, right? So if we do the unit analysis, we have Newton kilogram squared and then divided by meter to the 4th, right? This one is not going to have any units. It's going to cancel, right? So only this is going to carry units. So then you're going to have here kilogram squared cancel. Meter squared cancels the meter to the 4th. So you have units of Newton over meter squared, which is pascals, right? So that's actually perfect. We want it to be pascals. Okay, so let's put all of that in. So now if we divide that by the pressure, the atmospheric pressure at sea level, right? We call that atmospheric pressure 1.013 times 10 to the 5th pascals. That's atmospheric sea level pressure. Look at the pressure at the center of the Earth, which is much, much bigger than that. So we divide that by the 1.013 divided by 10 to the power 5. That's going to be 1.7 million atmospheric pressures. 1.7 million atmospheric pressure. So that's why the center of the Earth is actually solid, right? Even though it's so hot, it should melt, right? As you're going towards the center of the Earth, it's going to get hotter. So the mantle is a molten solid. If you go inside of that, it's a liquid. It's a liquid outer core. But when you go inside of the Earth, it's a solid core, right? So the structure of the Earth that we believe exists is that we have a liquid outer core, right? Why is it liquid? Because it's so hot. The material of the liquid outer core is so hot. The pressure is also big, but the temperature is more than the melting point. So it has turned into liquid, right? Then when you go inside of that, our best models predict that the inner core of the Earth is actually solid. Okay? Now, how could that be if it's even hotter than the liquid core? The temperature is increasing as you're going down, right? So why does it turn back into solid? Well, look at the pressure. 1.7 million bar, right? At the center of the Earth. That's crazy. That's amazing pressure. So even though it's very hot, the pressure is very high, the material turns back into solid because it's compressed by such hot pressure, by such high pressures, right? So now, what would the pressure be halfway? Halfway in, we said that the pressure is going to be 3/4 of the pressure of the core, right? So that's basically going to be 3/4 of that. So if we multiply this by 0.75, right? So then you're going to get 1.3 million bar. 1.3 million bar. So even halfway in, the pressure is high. But it's not high enough to turn the material into solid, right? The temperature is so hot that the material melts. So now what would we do if the planet can be modeled as a non-uniform planet, right? Non-uniform density. Okay, so non-uniform. Let's say the planet Earth can be modeled as a non-uniform density where the density is decreasing linearly, right? Something like this, kappa 1 minus r over 2r, right? So kappa is some constant that we're going to have to integrate for and calculate, right? Then you have 1 minus r over 2r. So what does this mean? When the little r is equal to 0, then the density is equal to kappa, right? When this is 0, it's just equal to kappa. So this is the density as a function of r. When little r is equal to big R, so when little r is equal to big R, that's 1 minus a half, then it's equal to half kappa. Okay? So it's a linearly decreasing density, means whatever the density of the core of the Earth, let's say the core of the Earth is made of iron, and let's say its density, the density of iron is about 9 grams per cubic centimeter, right? And then by the time you get to the surface, if the density is half of the density of the core, so if the density of the core was 9 grams per cubic centimeter and the density of the surface was 4.5 grams per cubic centimeter, and if the density can be said to be decreasing linearly, then we can do this problem and let's see what answer we get. This is a little bit more realistic for planets because usually planets' densities tend to be decreasing as you go outward, right? So then how would we do the pressure equation? So now we have to do a calculation for the gravity G inside of that planet as a function of R, right? We have to derive another equation. And then we have to also solve for kappa. So let's see how that would work. G of R would be equal to Gm prime over R squared, right? So then we have a planet like this. Imagine you're at a certain location and I want to find the gravity G as a function of the little r, right? What would the gravity G depend on? Well, it would depend on the radius r and the mass of the planet that is inside of you, right? M prime is the mass of the portion of the planet that is inside of the little r, right? So then how do I find that? Well, I can say dm is equal to rho dv, then integrate that, m is equal to, and then rho is equal to kappa 1 minus r over 2r, dv is 4 pi r squared dr, right? And then you integrate that from what? 0 to r. 0 to r. This is going to tell you how much mass is inside of any location of any radius little r, right? So then we're going to integrate that. Okay, so then we're going to have here m is equal to, then the 4 pi kappa comes out. Okay, then I can take the r squared, put it into the parentheses. So then I have here r squared minus r cubed over 2r. And then we have dr, right? And then we're going to integrate that. So we're going to have here 4 pi kappa, then the integral of that is r cubed over 3 minus r to the 4th over 8r, right? Then you're going to have here from 0 to r, so that when you do it from 0 to r, it just comes out itself, okay? So the mass m prime is going to be equal to 4 pi kappa r cubed over 3 minus r to the 4th over 8r. Okay? So now, what is the kappa? We have to do another integral here. This is going to be the m prime. It's the mass of just the portion that is inside of you, right? The total mass of the system is going to be what? Okay, the total mass of the system is going to be the integral 0 to big R, kappa 1 minus r over 2r times 4 pi r squared dr. Okay? So it's going to be a similar integral, except you're integrating all of the radius of the planet, right? So then you're saying here 4 pi kappa integral 0 to r, then the r squared goes in, you get r squared minus r cubed over 2r dr. So same integral as we had here, right? Then the integral is going to be the same answer, right? So you have here big M is equal to 4 pi kappa r cubed over 3 minus r to the 4th over 8r. Then you integrate 0 to big R. Okay? Then you put the big R in there. See the difference here, we put here little r, right? To calculate the m prime. Right? So then we put in the big R in here. We get here 4 pi kappa. And then we get here r cubed over 3 minus r to the 4th over 8r. Okay? Now notice what happened. When you did this, we can actually combine these two, because one of the r's cancels this and you get r cubed. So you get r cubed over 3 minus r cubed over 8, right? So then you can put it into here. That will give you a value for m prime. All right, so m prime is going to be, let's put it here like this. Four pi kappa is going to be 24m over 5r cubed. Okay, then you have here r cubed over 3 minus r to the 4th over 8r. Okay, so then that gives you the portion of the mass of the planet that is inside of any location little r, and then the g is going to equal gm prime over r squared. So you just divide this by r squared, then you're going to get what here? 24m over 5r cubed, and then if you divide this by r squared, you're going to get what? R over 3 minus r squared over 8r. So that's the value of g as it depends on the little r. Now the way that you know that you did it right is when you put here little r is equal to big R, the g value that you get should be gm over r squared, right? So if you put little r as big R, gm over, let's combine this, 24mg over 5r cubed, and then this one is going to be what? R over 3 minus R over 8, which is going to give me 5R over 24. Okay, this 5 should cancel this 5, the 24 should cancel this 24, and you get GM, and then one of the R's cancels this, and you get GM over R squared. Right? So the gravity at the surface of a planet, no matter the density distribution of that planet, is always GM over R squared, right? So then, what I'm going to do, take that value, take that function of G that we got, this function of G, put it into our pressure equation, right? So then I'm going to have here, replace this by 24gm over 5r cubed, right? And then put in this function, r over 3 minus, and then replace kappa by what it was. What was the value kappa? Well, remember 4 pi kappa was that value here. So we have here dp is equal to 24m over 4 pi 5r cubed. Okay? So all I have left to do is perform that integral and then evaluate it from little r to big R, right? Now to make this a little simpler, what I'm going to do is I'm going to just calculate what the pressure at the core of that planet is, right at the center of the planet, right? So instead of doing R to R, I can just go from 0 to R, right? If I did little r to r, that will give me a general equation for the pressure at any point along that planet. But if I'm interested just in the pressure in the center of the planet, I'll go from 0 to r. So the integral of this is going to be r squared over 6. Actually, we can combine these two, right? Before integrating it, minus r squared over 8r minus r squared over 6r, what is that? Well, it's like doing r squared over 8r plus r squared over 6r, right? So what is that going to be? The common denominator is going to be 24. So I multiply this by 3, multiply this by 4, right? So then it's going to be here 3r squared plus 4r squared over 24r. Right, so then it's going to be 7r squared over 24r. Right, so then I can just write this as negative 7r squared over 24r. Okay, so then the integral is easier because we get here r squared over 6, and then we put here r squared over 6 minus 7. If I put here big R, right, what's going to happen? It's just going to be 7 over 72 big R squared, right? So 7 over 72 R squared, right? Plus, and if I put big R here, I'm going to have R squared over 64. So plus R squared over 64. Okay? So if we combine all of this, notice that these are all the same thing. We can just combine their coefficients. So we can answer that we got for the uniform planet. The uniform planet was, right? So what is this going to be? Well, gm squared over pi r to the fourth, this thing is the same. Gm squared over pi r to the fourth. The difference is the 24 squared, the 0.085, and the 100, right? So if I square the 24 divided by 100, I'm going to get 5.76. 5.76 multiplied by 0.085 is going to be 0.4896. So the pressure, 0.4896. So all of these things, this and this comes out 0.4896. Then you have your gm squared over pi r to the fourth. Okay, what's the 3/8 come out? All right, the 3/8 comes out 0.375 gm squared over pi r to the fourth. The pressure at the center of this planet is higher than the pressure at the center of a uniform planet, right? You see that? 0.4896 times all of this stuff. This is 0.375 times all of that stuff. Does that make sense? Always ask yourself, does it make sense? Compare the two numbers and see what is happening. Okay? What did we say? The planet is denser at the core of the planet. And as it's going out, less material, the material weighs less, right? So the center is the densest objects, and as you get farther out, it gets less and less massive, right? So if I want to find the pressure at the core, all of that material that is close to the core weighs a lot and pressing down on it, right? It makes sense that since this is very heavy at the core, near the core, the pressure there is going to be very high, more higher than if the mass was uniform density. Because uniform density, what would happen, the objects here would weigh similar to the objects inside, but they would have a much bigger area. So the pressure would be, the weight will be distributed over a larger area and the pressure will be less, right? But if more weight is concentrated at the center, the surface area of the center is smaller. That means the weight is distributed over a smaller surface area and the pressure is higher. So it makes perfect sense. So this is more likely the case for the Earth. Something like this, right? So then what is it going to be? The pressure, instead of being 1.7 million bar, it's going to be higher by what factor? So then I can multiply that by the factor of 0.4896 divided by 0.375. So just do a ratio thing. Now you can all imagine what the pressure at the core of Jupiter is, the pressure at the core of Saturn. They're so strong, so humongous, that when our satellite Galileo plunged into Jupiter, that it was literally crushed by the weight of Jupiter's pressure before it even got to the core. Maybe it was 20% of the way down, or 30% of the way down, and it already was crushed by the strong pressure, okay? The pressure there is so strong that it even turns liquid hydrogen into liquid metallic hydrogen, okay? It's a form of matter that doesn't exist here on Earth. It's called liquid metallic hydrogen. So you can kind of see now how we can model these planets with different density functions and then find out what their pressure variation as a function of R is, and then calculate the pressure at their centers. Thank you very much.